Hey guys, this is Angel, and today we're going to be going over a bit of a tougher projectile motion question. And I apologize if it's kind of long. This is a little bit tougher of a question that requires a lot of conceptual understanding. But as in going through this question, you'll hopefully be able to really understand what's going on conceptually with these problems. And so let's just go ahead and get started right away. A sprinkler shoots water at an initial velocity of 20 meters per second at an angle of 35 degrees to the horizontal. A light post stands 25 meters away from the sprinkler. At what height above the ground does the water hit the light post? If the water does not hit the light post, what is the range of the water from the sprinkler? All right, so first thing we got to figure out is the water traveling far enough? Is it traveling at least 25 meters to hit the light post? And so in order to do that, we're going to need to solve for our vertical and our horizontal components of the initial velocity like we do with every projectile motion question. And when you do that, you get that the vertical component is about 11.5 meters per second, and the horizontal component comes out to be about 16.4 meters per second. If you don't know how I got that, I was just solving for using the trigonometric functions to solve for these components. The first video goes over that thoroughly, but now we've got that. And what can we use this right here, this vertical component of the initial speed to solve for? And the first thing that you should come to your mind is you can use it to solve for the total time of the projectile in motion. And so that's what we're going to go ahead and do next. So the equation that I'm going to be using is going to be the delta x equation that involves the acceleration of gravity. But we're going to call it delta y just because we're dealing with the y-axis, right, the height. So we're going to call delta y equals the initial velocity, which we've determined to be 11.5 meters per second. Initial velocity times time, which is what we're solving for because we want to know how long this projectile is going to take. And then we're going to subtract 5 meters per second squared, and that's because you would do 1/2 of the acceleration, and 1/2 of the negative 10 meters per second squared is going to be negative 5 meters per second squared, and then that's going to be multiplied by t squared. So now what we're going to want to do is set our delta y equal to 0, and we went over that in the previous problem, and the reason we're setting it equal to 0 is because the projectile is going to look something like this. And so there's going to be 2 points where the y-axis is going to be equal to 0 meters. The first one being 0. If we were to multiply this by 0, if we were to input 0 for t, we'd get 0 there, minus 0, answer would equal 0. But we're looking for that time that is greater than 0 that will also give us a delta y of 0 meters, or a displacement of 0 meters. So we're going to go ahead and, now that we've plugged that in, 0 meters there, we've got 11.5 meters per second times t minus 5 meters per second squared t squared. And this is where we do a little bit of algebra. So because both of these components of the difference have a t variable in them, we can take out that t and separate it to look like this. So we would take out a t, and that leaves us with 11.5 meters per second, and we took out this t, minus 5 meters per second squared, with 1 t left over from this t squared. So now if we were to input 0 here, 0 times anything is 0. And so what we want to solve for is what value of t here will make this whole quantity equal 0. So what we can do, and we're going to treat this as a separate, we can do is set that within the parentheses equal to 0 and solve for t. And when we solve for t, you get that t equals 2.3 seconds. And so in there, what we would do in that case is subtract the 11.5 to the opposite side and divide by negative 0.5 meters per second squared, and then t equals 2.3 seconds. So we've got the total time of the projectile figured out. And now that we've got that, we can solve for the range because we've got the horizontal component, and we've got the time of the projectile, And so just eyeballing it, 16.4 times 2.3 is definitely greater than 25 meters. It's something around 30, it's definitely greater than 32 meters. And so we know that the water does at some point hit the light post. Now what we need to figure out is how high above the ground does it hit the light post at. I'm going to go ahead and erase all this. And so how would we solve for that? Well, we want to figure out how long it takes the water to travel those 25 meters. Because if we know how, wait a second. So we want to figure out how long it's going to take the water to travel those 25 meters. Right? So now that we've got our total time of the projectile, we know that it is going to travel greater than 25 meters, but how long is it going to take to get to the 25 meters? And we've got a horizontal component of the initial velocity, and we've got a distance, so we can solve for time using our velocity times time equals distance equation. So the 25 meters is equal to our velocity, which in this case is 16.4 meters per second because we're now dealing with the horizontal, and then times time. So what we would do, we would just divide the 25 meters by 16.4 meters per second, and then the units would resolve to 1.52 seconds. And so what we just solved here is that at 1.52 seconds, the water is 25 meters away from its initial position. It's traveled 25 meters in distance, and it is 25 meters in displacement. Now what we're going to do to solve for the height is we're going to go back to that equation that we used earlier, which was the delta y equation, delta x on our equation sheet, but you definitely want to memorize your equation sheet. And so now what we're going to do is use that same equation, but this time we're going to plug in the time and solve for the height. We're going to solve for the delta y. Because we've got our initial velocity, which now that we're dealing with the vertical, so always keep in mind, are you dealing with the vertical or the horizontal? Now we're dealing with the vertical. Then we're going to put in 11.5 meters per second, and then we're going to plug in 1.52 seconds, and then minus 5 meters per second squared times 1.52 seconds squared. So you can solve that using your calculator, or you can solve it algebraically, and then you would get that delta y is equal to about 5.9 meters. And so now we've gone through the process of solving for the height at which the water is going to hit the light post, which comes out to be 5.9 meters. If you were writing this short answer, you would say yes, the water from the sprinkler will hit the light post at approximately 6 meters above the ground. So just to recap everything, that took a little bit of calculations. The first thing we had to do was solve for the total time of the projectile, and that ended up being about 2.3 seconds. And then when we solved for the total time, we knew then that it does go above 25 meters. And so there is going to be at some point that the projectile hits, which we solved for being 6 meters, but we only were able to solve for those 6 meters after, right? So after we determined how long it was going to take to travel the 25 meters of the distance from the light post. Then once we solved for that time, which was 1.52 seconds, we were able to simply just plug that in with our initial component of the vertical velocity into the delta y equation with gravity as our acceleration, and determine that it will hit the light post at about 5.9 meters or 6 meters if we were to round up. And the MCAT would give you the 6 meters as one of the multiple choice answers. So just to recap everything, this was a rather long question, and before we were able to start determining whether the sprinkler was able to hit the 25-meter light post, we had to first solve for the total time of the projectile, which ended up being about 2.3 seconds. Once we've got that 2.3 seconds and looking at our horizontal component of the initial velocity, which was roughly 16.4 meters per second, we were able to determine that that would definitely go above the 25 meters distance of the light post. When we knew that, we then solved for the amount of time that it took the water to travel to those 25 meters, which in that case ended up being about 1.52 seconds. And then once we had that 1.52 seconds, we had our vertical component of the initial velocity. We were able to simply plug into the delta x, or we use delta y equation to solve for the height of the water at the 25 meters at the time of 1.52 seconds. So there was a lot of conceptual stuff in this problem, but you have to just take it step by step. And there are things that you need to solve for first before you're able to solve for other components of the problem. So I really hope that that helped you guys out. Definitely recommend watching this video once or twice. I would also look into other online forums for similar questions, because this is a type of question that I have noticed a lot of people have problems in, because they haven't necessarily determined the right way of finding one part of the problem before finding a different part of the problem. And so hopefully this helped you out. If it did, if you have any questions, leave us a comment below. Make sure to subscribe for weekly updates to the videos. Thank you so much, guys.